In this video, I'll show you some strategies for the preparation of activated carboxylic acid derivatives, followed by their reduction to alcohols without isolation of the activated intermediate. The addition of hydride or hydrogen to the carbonyl group of carboxylic acids should proceed more readily if electron density is removed from this carbonyl group by some electron-deficient activating group. Typical examples of suitably activated carboxylic acid derivatives include acyl halides, mixed carboxylic carbonic anhydrides, hydroxybenzotriazole esters, mixed carboxylic cyanuric anhydrides, and substituted phenyl esters. Ideally, this group should of course not react with the reducing agent, as this would increase the required amount of reducing agent. The main advantage of this strategy is that milder reaction conditions are required to reduce activated acid derivatives than unactivated ones. Except perhaps the reduction with borane, most reductions of carboxylic acids require harsh conditions or powerful but unselective reducing agents, such as lithium aluminum hydride. Activated carboxylic acids, however, can be readily reduced, often with high selectivity. Moreover, one hydride equivalent less of reductant is required for the reduction of a carboxylic acid derivative if compared to the free acid. Disadvantages of this strategy are the larger number of reagents required and its higher complexity, as essentially two different reactions must be performed. Also, a larger amount of waste will generally be produced, what will further increase the cost of this strategy. In this example, protected glutamic acid was activated by conversion into a triacenyl ester by treatment with cyanuric chloride and a weak base. Removal of the amine hydrochloride by filtration can be beneficial because the reducing agent may also react with the amine hydrochloride to yield hydrogen and the amine. Here, only 1.5 equivalents of sodium borohydride were sufficient to bring about a complete reduction of the active ester, without any significant reduction of the benzyl esters. In this example, the carboxyl group was activated as mixed carboxylic carbonic anhydride by treatment with ethyl chloroformate. These mixed anhydrides must be kept cold because at room temperature decarboxylation usually occurs and causes the formation of an ester, an ethyl ester in this case, which is much less reactive than the anhydride. Again, the activated intermediate could be reduced with sodium borohydride at low temperature, which gave a high yield of the expected alcohol without epimerization or lactone formation. In this example, activation was again achieved by treatment with a cyanuric acid derivative. The resulting intermediate was, however, reduced by catalytic hydrogenation with palladium on charcoal. Despite conducting this reaction in ethanol, no ethyl ester formation occurred. So what can go wrong? One potential side reaction is the incomplete reduction of an active ester to give mixtures of alcohols and aldehydes. Unlike the reduction of free carboxylic acids, where the first step is usually the slowest, in the reduction of active esters the first reduction step may be the fastest, what might enable a high-yielding preparation of aldehydes. Then, activated carboxylic acids readily react with all kinds of nucleophiles, including water, alcohols and amines. Again, the corresponding products would be less reactive than the activated intermediate and will probably not be reduced as smoothly. Finally, as mentioned above, mixed carboxylic carbonic anhydrides decarboxylate at room temperature and must therefore be kept cold. Here are some more examples, and many more have been reported. Although this method is easy to perform in the laboratory because of the ready availability and stability of most reagents, for larger scale preparations, a reduction with borane or sodium borohydride in combination with an electrophile, as discussed in an earlier video, will probably be superior.